Well, welcome everybody to our third lecture. We're going to do some more modeling of word problems today. Should be good. Anyway, unless there are any questions right off the bat, we'll just jump into it. Great. All right. Is my pen working? Excellent. So we're going to open with a classic problem in the operations research sphere, the knapsacking problem. So a company, I think this comes from the book, doesn't it? Company wants to ship some crates between two cities, and they have a freight car. They have 6 different types of crates that have different weights and values. And the container that they're shipping this in has a maximum capacity of 1,000 kilograms. So we want to formulate this problem of finding the most valuable shipment as an LP. So how do we fit the most value into 1,000 kilograms from this data? So we'll start, like usual, by defining our variables. Xi is the number of type I crates shipped. For I in 1 to 6. And my notes have gone away. And the objective is to maximize value. So maximize value times our x vector. 60x1, 70x2, 40x3, 70x4, 20 x5, 90 x6. And over here, that's going to be behind, that's going to end up behind my head. Well, let's let W transpose equal the vector of correction. Let V transpose equal that vector. W transpose equal that vector. I write this transpose here because I don't like row vectors. If you use them, no big deal. A lot of people use them. I don't like them. But there's another way, there's a more compact way maybe to write this LP. And I'm just going to put it over here just so we can see it. Maximize value transpose X. Subject to our constraint. Our weight cannot exceed 1,000 kilograms. So again, very similar to stuff we've seen before. Plus 30x5, 70x6 is less than or equal to 1,000. More compactly, we could just say weight transpose x less than or equal to 1,000. And then we need our non-negativity, our domain constraints. Xi greater than or equal to 0 for all I in 1 to 6. Same up here. So that's two relatively that's two different ways to write this formula. The nice thing about this smaller, more compact version is that, say you're writing this up in a program, you can define your w's and your number of x's in just a single vector, and then you can change those on the fly without having to go in and change the whole model, the whole script. So that's very similar to stuff we've seen before. This is called the knapsacking problem because it comes from the idea that you want to put the most valuable things, if you're going on a trip, you want to put the most valuable things you have in your knapsack. And your knapsack has only a limited capacity. Very classic problem. Used in a lot of different spheres. But I have a question about this. Is it really appropriate to let our decision variables take fractional values in this problem? So I didn't include an integer constraint in here. And the question is, do I need one? Well, yes and no. To be perfectly accurate to the problem, to be perfectly correct, yes. To be exact, we need xi as an integer. But what's interesting is that this problem, in its current form, without the integer constraint, has I don't want to call it obvious, but it has a solution that we can find by ourselves. What if we just take the weights, or the values, divide them by the weight, and find the density, or the value density of each item, each crate. Well, value density is going to be our how much value per kilogram can we stuff into this shipping car. And it turns out that item 2 has the highest value density. My notes are not showing up. So, what did I say? X2? X2 has the highest value density. Has the largest V over W. So the solution is simply get as much x2 as possible, as fits. So pack maximal x2. Well, we have that the weight 2 equals 20. Let me rewrite this a different way. So our first constraint, or our only real constraint, is this weight constraint. But if everything else is going to be 0. If all of our other variables are 0, this collapses to 20 x2 less than or equal to 1000, which tells us that x2 equals 50. That happens to be an integer. Right? So that's great. We didn't have to impose any integer constraints. And our solution came out as an integer. Excellent. What if, though, instead of 1,000 kilograms, our car could take, what if capacity of 1,015 kilograms? Well, suddenly we get a fractional thing here. We get that x2 equals 50 3/4. Well, that's fractional, but if we look back here, none of our other variables have a weight less than 15 kilograms. So nothing else can fit in our spare space. It's possible that there could be a better solution. It is possible that another solution could be better. But if we just round down, we're not losing very much. It's still pretty close to optimal, just by rounding down. Maybe you or whoever you're consulting for doesn't care about a little bit off the top being lost. Maybe they just want something close to optimal. In that case, we can ignore our integer constraints. For this type of problem, you have to make that decision for whatever problem you're looking at. And the reason we might want to do that is because integer variables make the problem much, much more difficult for a computer to solve. If we have one integer constraint or variable, it's not a big deal. But if we have 200, 200,000, however many variables, suddenly it's much more difficult. So there are instances where ignoring integers is a boon. Anyway, let's move on to there we go. Now it's showing up. Great. So let's suppose that Kitchtech, the company, cannot send more than 10 of any single type of container. What does that constraint look like? Well, that's pretty clear, right? xi less than or equal to 10 for all I in 1 to 6. Or x vector less than or equal to 10 times the 1 vector. That's how I would write it, because I'm, again, a snarky math major. This just means 10 times the vector of 1s. So it's really the vector of 10s. That's pretty clear. I think we've done constraints like that before. What about this? Kitchtech may only send type 3 containers if they also send a type 4 container. Well, this is a logic constraint. This is one of a few types of logic constraints. It's an if-then. So what we want to do is we want to say if x3 greater than or equal to 1, then x4 greater than or equal to 1. Or maybe you might prefer the contrapositive of this. If x4 equals 0, then x3 equals 0. These are equivalent statements. They're related by what logicians call the contrapositive. But all you need to know is that these statements are equivalent. So how can we accomplish this? Well, the book has an answer for us. But I'm going to generalize on it a little bit. x3 less than or equal to capital M times x4 for a sufficiently large M. So what does this do? What does this do? So if x4 equals 0, so let's do this. If x4 equals 0, then we get x3 less than or equal to m times 0 equals 0. So x3 has to be less than or equal to 0. And we've already said that it has to be greater than or equal to 0. So x3 equals 0. Great. That's exactly what we wanted, right? If x4 greater than or equal to 1, then x3 is less than or equal to m. Well, let's actually just do an equal to 1 for now. If it's equal to 1, then we get that x3 is less than or equal is equal to m, or is less than or equal to m. So how big does m need to be for this to be valid? Well, in the previous step, we said that we could only send 10 of any type. So for including the last constraint we just did, m equals 10. Works just fine. Because this would then look exactly like the constraint we just wrote down on the previous slide. If we didn't have that constraint, x3 has a w3 equals 30. So m equals the maximum x3 can be. So 1000 over 30 is 33 repeating. That's also valid. Really, yeah, even, I'm getting behind my head here. We could even say m equals 100 or 1000 or 100, whatever, however many you want. You can do that. You might run into some issues with overflow if you have a too big of a number and you're trying to code it into a computer. But it's a valid constraint nonetheless. Additionally, if you're using an integer variable, you might run into, what was I going to say? You're going to have a tighter approximation the smaller m is. M has to be big enough that we're still enclosing our feasible region, but you ideally it's small enough that we have a tight sort of approximation of our feasible region. if that makes any sense. If it doesn't, don't worry about it too much. That's more of a topic for DOR2. Anyway, we have another type of logic constraint that is presented in the book that I want to go over here. I simplified it a little bit from the book's example. So we have to send at least 4 type 1 crates, or at least 3 type 4 crates. So let's write that out logically. If x3 less than 4, then x4 greater than or equal to 3. Additionally, we also need to satisfy its sort of related statement. If x4 less than 3, then x3 greater than or equal to 4. We need both of these statements for this type of constraint. But we'll see that we can follow the logic through one and it'll satisfy the other. So we do this by including what I like to call indicator variables. I tend to use Greek letters for indicator variables. The book in this example used y, which is perfectly fine as long as you say what the variable is. So d, or delta, 1 if x3 is 1 and 0 otherwise. Is that correct? No. No. If x3 is greater than or equal to 4. That's what I want. And then we have this constraint, x3 greater than or equal to 4 delta. So what does this do? This tells us that if delta equals 0, then x3 greater than or equal to 0, which is a constraint we already have in our problem. It is x1. You're absolutely right. If I can press the right button. I was stuck on the last page. Then x1 is greater than or equal to 0, and we haven't added any new constraints to the problem. If delta equals 1, then x1 greater than or equal to 4. And that is a new constraint, which is nice. So then, what else do we want to say? If delta equals 0, then x4. So if delta equals 0, then x1 is not constrained. x1 can be whatever it wants. So then x4 needs to be at least 3. So we're going to use a very similar constraint, x4 greater than or equal to 3, 1 minus delta. This inverts our indicator function and says that and satisfies this statement. So the things we add to our program are going to be x1 greater than or equal to 4 delta, x4 greater than or equal to 3, 1 minus delta, and delta is binary. Again, there are several ways to write this binary domain constraint, and however you want to do it, that's fine. Just make sure it's in there if you have a binary variable. So this is what we add to our IP or LP or what have you. This is not obvious, so if you didn't follow this, it's because it's difficult. The book, I think, does a decent job of explaining it. Go back and reread that. Watch me explain it again, or come ask me in office hours. We won't be doing a ton of this kind of work in this class, but I think it's an important feature of IP for you to have at least seen. So, does anyone have any short questions on it at the moment? All right. We'll move on to another type of problem. Set covers. So if we have a matrix, and this matrix could represent a whole slew of different problems, real-world applications. So matrix A and a vector of weights in the same dimension as the number of columns. We say that a column covers a row if the entry in that column row is 1. So this column covers these two rows because there's 1s here, but it doesn't cover the top or bottom row because there are 0s there. So column 2 covers rows 2 and 3. So we want to select a subset of columns such that each row is covered by at least one column in S. This is called the set cover problem, and it has a whole slew of applications, so many that I don't even want to give an example, I guess. Anyway, we're going to say Sj. Let me think of an example as we work. If column J is in S, otherwise it's 0. So we want to minimize the cost of our cover. So I'm going to say cost transpose S. Subject to that, well, yeah, subject to this vector again, this notation is convoluted purely because I do not like row vectors. I like my vectors to be vertical, and I throw in this transpose to accommodate that. So let me translate this for you. Well, first I need to put in our binary constraint, or even better, it should be n here. Let me translate that for you into something maybe more familiar. Minimize the sum, j is 1 to n, cj, sj, such that j equals 1 to n of aij, sj greater than or equal to 1 for all I is that what I wanted? No, in fact, I think I want an I here instead. And this should be a vector. No? Wait. That column, or that row times that. Yeah, that's what I want. And I want an I there for all I in 1 to m. And we're getting dangerously close to my head there. And then s is in 0 to 1 for all j in 1 to m. So what I've said here is in every row we want, let me change to a different color, we want the row times how many times our s vector, or dot product with our s vector, to be greater than or equal to 1. So this says s1 times 1, s2 times 0, s3 times 1, s4 times 0, s5 times 1, s6. So s1 plus s3 plus s5 has to be greater than or equal to 1. So our cover has to include at least S1 of S1, S2, and S5. And that's the same for every row, every I up to M. It's going to be a slightly different expanded form, but this is how that expands out. feel like maybe I over-explained that. Um, is anyone caught up in my web of tangential explanations? No? All right. Feel free to type it in the chat or speak up if you decide that you are.
For the second, like minimum, where it's the sum of,
Yeah,
yeah, so where it's such that, what is above the sigma? Is that an N or is that a C?
that's an it should be an N
Okay, okay, thank you.
because I'm summing over all of the columns J, and there are N columns. Always feel free to call out my handwriting or my spelling or what have you. Um, my spelling is bad. All right, then moving on. Let's do another in-class exercise. Um, I'm going to give you guys more time, and I'm going to do a little more build-up to maybe give you a place to start from this time, and we'll see how it goes. So, a mining company. This comes from the book. This is one of the exercises that I should have labeled in the slides. Uh, 2 point, well, 1.3 exercise 10. So a mining company just completed a survey of their newest open pit mine, and they want to make sure that it's safe as they dig down. Each of these blocks, say 6 here, can only be mined if both of the blocks above it have been completely mined out. Each of the blocks has a value, mi, and we can only mine 7 blocks. And we want to maximize the value of everything. So I'm going to say let's let xi be equal 1 if block 1 is to be mined and 0 otherwise. So to reiterate, our constraint is 6 can only be mined if 1 and 2 were also mined. 7 can only be mined if 2 and 3 were also mined. So I'm going to set you guys loose for 10 minutes in some breakout rooms, and we'll see if give you a chance to think about it yourselves before I go over it in detail. Figure out where the breakout room button is. Recreate. Alright, and I'll share this screen again to the breakout rooms. Where is the screen? E.
Hi, Professor.
Yes.
Yeah, the problem
Is
isn't showing on our
is it
screens.
not? Let me let me fix that then. Thanks for bringing it up.
Yep. I'll join back to the breakout room.
Well, what do we think about that? Was the little extra time and the build-up helpful? Was that more engaging? Was that worth it? Great. Odin thinks so. Well, be sure to leave any feedback, in the Google form, if that's something you're passionate about. And let's go ahead and go over, go over the problem from my perspective. All right. So the objective we've seen in, let's do it in red actually. The objective we've seen in several varieties already. Maximize the value times whether or not each block is mined. Subject to, first I'm going to say x1 plus x2 plus x12 less than or equal to 7. Oh! Haha. I forgot to swap scenes. Great. Thanks for letting me know. Where did my mouse go? You can see that now, right? I just use a dot 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 here and ellipses to tell us that we're summing up all of the variables in between. That's okay for a lecture. I wouldn't recommend it on a homework or a formal report. But that's our we can only mine 7 of the blocks. So that's that constraint. So what about the constraint that we can only mine 6 if 1 and 2 were mined? Let's see, x6 is less than or equal to a is this a big M? Yeah. Now I don't like this notation, so we'll simplify it in a second, but I wanted to show you that it's the same kind of idea. What is the importance of having M transposed? Excellent question. So a vector, or this is the same as the dot product. These are equivalent. So some people will forgo the transpose and you'll just assume that it's a dot product. I like to include the transpose just because then it makes vector multiplication and matrix multiplication the same operation. I'm a stickler about it for myself. I don't particularly care if you guys end up using this notation or the dot product or whatever. But I like to be thorough. So this, I just wanted to show off that it's the same kind of idea as our big M constraint from earlier. And maybe M is a bad example here because we already have an M and my capitals look the same as the lowercase. Let's call it a W instead. So we want to say if x1 plus x2 less than or equal to 2, then x6 or correction, strictly less than 2, x6 equals 0. That's sort of what we want to say. But since x1 is binary, all we have to do is if x1 plus x2 equals 2, then x6 is less than or equal to 1. So if we mine 1 and 2, we could mine 6. If we mine 1 or 2, that sum equals 1, we cannot mine 6. So that's the logic we want to enforce. So in this case, W is sufficient to say W equals 1/2. I did x1 times x2 is less than 1. Okay, that's an excellent question, and I'll need another. Well, so that does accomplish the same logic. However, it's not linear. So we have a question: if x1 plus x times x2 is less than 1, then x6 equals 0. So this does accomplish the same task. However, x1 times x2 is quadratic. It's not linear, and so it won't fit in a linear program. Since these are binary in variables, there are ways to enforce a quadratic like this linearly, but I'm not going to discuss that in this class just because it's a little bit high level and it's more suited to DOR2. But that's a very good question. So if we let W equal 1/2, then that's going to be sufficient. And yeah, so maybe another way to write this, if we want to move all of our variables over to one side, negative 1/2 x1 minus 1/2 x2 plus x6 is less than or equal to 0. So I just subtracted the right-hand side over and put it in index order for the sake of things. And then we're going to have a similar constraint for every other block. And of course, we also need our xi is binary. Very important. So that's going to get a little messy quick in this sort of notation, so I'm not going to write out the whole thing this way. But I want to show you that we can define a matrix. In this case, I called it A, that will enforce all of our constraints sort of in one little piece of notation. So here we have our first row is the sum. Well, let me subject to ax less than or equal to my keyboard has just decided it doesn't want to cooperate. There we go. Less than or equal to b. This encapsulates all of those constraints in a single piece of notation. Of course, you have to define a and b, but what this says is the first row is just going to be the sum of all of our x's less than or equal to 7, which is exactly what we had here. Then our second row, negative 1/2 minus 1/2, and then 6 is 1, so that's going to be negative 1/2 x1 minus 1/2 x2 plus 6 is less than or equal to 0, which is the same constraint I wrote here. And then we have the same sort of constraint for all of the blocks. You'll notice that at 5 we move on because we've breached the first row and we have a new row to think about, a new row of blocks. But we have the same kind of idea of constraint going all the way down. And we have, just like we had earlier, maximize M transpose X, and X is binary to 12. If you're not familiar with raising a set to an exponent, this just says that this is a vector of size of dimension 12 with entries being binary, 0 or 1. So this is a very nice, succinct way to write any linear program. And I do mean any linear program, because in fact, any LP can be written in this form. The one caveat to this is that if you have any constraints with equal signs, you're going to have to define a new matrix specifically for equal signs. Unless we have equality. That's behind my head. Constraints. Now, this does not give you free rein to, on your homework, just write down AX less than B. And I don't mean the binary. Not every LP can be written as a binary program, but we might. You do need the domain clause there. So this doesn't give you free rein to just write AX less than B on your homework problems and be done. You do need to define, if you're going to write it in this form, you do need to define your A, your capital B, and your vectors. And we'll be exploiting the fact that LPs can be written like this to actually solve them later on in the class. So it's important to understand how this is working. If you're struggling with it, if I'm making it unclear, drop me a line at some point, and I'll try to explain it to you one-on-one. Unless there are any questions right now. All right. All right. Nothing then. Let's move on to a slightly different topic. I've covered the basics of when you use integers, how you use integers, how to write a matrix form. Oh wait, I have one more slide here. Do I have time to talk about this? Let's move on instead. I'll bring this up in a future lecture. Let's talk about graph theory for the last 10 or so minutes. A graph is a mathematical idea used to model communication networks, road connectivity, social media, just whatever. Really tons and tons of things. A graph consists of a set of vertices, sometimes called nodes, if you get confused about the plural of vertex, like I do, and a set of edges in the multiplication of the vertices squared. If you haven't seen this before, this is a subset symbol. A set is just a list of entries, and a subset is just a list of some of those entries. So this is the example that they used in the book. We have 5 vertices labeled 1, 2, 3, 4, 5, and the edges 1 to 2, 2 to 3, 3 to 4, etc. Now, maybe the confusing thing is that edges are bidirectional, so 1 to 2 is the same as 2 to 1. And I don't particularly like their notation here because 1, 2 could also be read as 12, which is not great. It's more clear if this was labeled with letters rather than numbers. I typically write this as a nested set. 1, 2, 2, 3, 3, 4, etc. down the line. This indicates to me that because sets are orderless, they're the same set regardless of what order you put them in. This indicates to me that these edges are both bidirectional and sort of a set of, they sort of indicate an edge between two objects. However you want to do it, whatever makes sense to you, go ahead. Again, I'm being a stickler for clarity here, but so some graphs also include weights for vertices or edges. So we could say, you'll notice that we have edge 1, 5. That corresponds to the line between 1 and 5 when we draw these out. We could have weights associated with edges or vertices. These could be lengths or costs to produce or umpteen other things. But the important, well, yeah, they could be whatever. They could represent many, many things, but we could have weights on any element of a graph. Also, graphs do not usually have a canonical way to draw them. If your graph is a map of the US and roads connecting it, connecting cities, you may want to write it or draw it so that it looks like the US. But in our case, we don't have that, so we could draw the same graph however many different ways we want. As long as all of the edges and all of the nodes are present, it doesn't really matter. In our homework, we have a graph that has duplicate edges. That's fine in some contexts. In other contexts, it's not. And you don't need to know the details of that. That'll be apparent by problem. But that's the idea of what a graph is. Let's real quickly talk about Skip that. That's in the book. Talk about... I don't think I actually have time to talk about this problem. So we'll pick that up some other time. But I think that's all you should need to know for the homework concerning graphs. Again, I'll stick around here for any questions, but that's all I have prepared for today. So you guys can peace out if you want, or ask some questions.
Thank you, Professor.
Thanks for coming. Kelly asked, we should be able to do all of the homework assignment now. Yes, I think I've covered everything in the assignment. Let me... Yes. Any questions from YouTube? Thanks for coming out to the live lecture. Alright then. See you, YouTube.